technically.
Okay. Hello, everyone. Thanks for inviting me. Be happy to be here. So this is a work about algorithms for matroids. I'll talk about log-concave polynomials and simplicial complexes as well. These are my wonderful co-authors. Quickly, Leo is my student at Washington. Nima Anar is a researcher, like postdoc researcher at Stanford, and Cynthia Winzant at North Carolina State University. So one of my plan in the talk is to tell you a lot of different concepts I learned through this project. Hopefully by the end, we'll see how these are all related to each other. So let me start by talking about matroids. Hopefully many of you have seen them. Okay, so what is a matroid? It's basically, like, I assume that you have a set of elements, 1 to n, and you have a family of subsets of these elements. These are called typically independent sets. And usually the way we define them in CS is that they have these two properties. Like they are downward closed. If a set is independent, every subset is independent. And they have this so-called property that if you have a bigger independent set, you can add something from the bigger one to the smaller one to get another independent set. So this exchange property says that all maximal independent sets have the same size. These are called bases. The rank of the matroid is basically the rank of, or the size of its base. We usually assume that the rank is R. And there are many examples. Some of them, like probably the most famous one is the graphic matroids, where you look at the independent sets are acyclic subgraphs or forests. Another famous example is the linear matroid, where you have a set of vectors, and an independent set is a linearly independent set of vectors. Okay. When you go to math, that's what I learned recently. They typically define matroids based on flats, but I'm not going to do that. But there are very different ways of defining them. They have very nice closure properties, which will be important in some part of this talk and other related works in this area. So these are some, like deletion, contraction, truncation. So what is deletion? It's similar to deleting an edge in a graph. So if you have a matroid on this graph, on basically acyclic subgraphs, you delete this edge, then you get a new matroid. It's the graph where this edge is removed, and you can again look at the independent sets of or the acyclic subgraphs of this graph, and that's a new matroid. Another example is the contraction, where it's the same as the contraction in graph that we know, right? So it's like you look at an edge, you contract it, and then like from now on, you look at independent acyclic subgraphs in the contracted graph. Okay. Truncation is when you sort of remove independent sets above a certain size. So you say, I only allow independent sets of size up to 10. And that, again, preserves matroids. OK, so just some closure properties. Now let me tell you about algorithmic questions, what CS people are interested in. Like the first question typically you want to ask is optimization. And basically the fact is that optimization is easy. So there is this nice characterization of the convex hull of basis of a matroid by Ed Bones back in like 50, 60 years ago. Basically, he says the following. Let's say this is a matroid. This vector 1 is orthogonal to these guys. These are all the bases. You can look at the indicator vector of each base. It corresponds to these points. You can look at the convex hull. This convex hull is very well understood. The edges are of the form 1i minus 1j. The facets basically have this kind of property that you look at a set of elements. You say that summation of x's on that subset is at most the rank of that set. Okay, so this is very well understood. You can study separation oracles for this. You can do optimization. You can optimize even a convex function over this. So this is we know all about it. Now so whenever you can do optimization, the next question is, okay, what about counting? If you cannot do optimization, you cannot count. But usually when you can do optimization, you can also count. So now this question was asked about 30 years ago by Mihail and Vazirani that, okay, given a matroid, can you count? Can you count number of bases of that matroid?
When you say count, you mean approximately count.
Good, yes. Yes, so there are many things. So first, what do I mean by given? So a matroid has exponentially many independent sets, typically in the number of its elements. So typically when I say given, it means that there is this oracle that if you ask if this set is independent, it says yes or no. Okay, so there is a Turing machine or oracle, whatever that answers your question. There's also this count problem that, okay, you can prove that you cannot count exact. So you want to see if you can count approximate. And if you can, with what approximation? There is this very nice work of Azar, Broder, and Fries, which actually says that if you want to count deterministically, you have to suffer a lot. You cannot do better than 2 to the omega of r, the rank of the matroid. So you cannot do better than some exponential in the rank of the matroid.
That's a factor by which you.
That's a factor of approximation, right? It's a multiplicative factor, yes. So this is the best you can hope for, and in this, so the reason they got interested in this is that they were hoping, so if you know about these results on estimating volumes of convex sets or polytopes, we know that deterministic algorithms cannot do better than exponential, and here they were trying to say, for this problem, deterministic algorithms cannot do better than exponential as well.
The optimization is easy part also assumes oracle access to the matroid.
No, actually, the greedy algorithm works perfect. So the thing is, matroid are exactly classes of objects that the Kruskal algorithm works. So because of that, optimization is also easy. But this is probably a more fundamental reason that it is easy. That this polytope is integral, has this nice structure. You can do all sorts of yes.
This is all for general matroids, but for specific nice matroids, can you do better, like linear or graphic?
Oh, for this?
Yeah.
So deterministically, you mean? I don't know.
It's an oracle result anyway. I don't think that
Yeah.
the oracle used in the lower bound gives you a linear matroid or a graphic matroid.
Yeah, the oracle is on the so-called paving matroids, so there are like exponentially many of them. I don't know any better result deterministically for graphic, matroids. But I agree that there could potentially be. Okay, good. So let me say one thing. So I want to talk about randomized algorithm for this problem. So that's the point of this talk, and that's the question we're going to study. Let me first say there is this duality which was known, again, many decades ago. There's this duality of counting and sampling. If you can count, you can sample, and vice versa. Okay? So I want to say one direction. The other direction is also straightforward. So let's say you can sample. Let's say there is an algorithm that can generate a uniform sample, uniformly random base of a matroid. I want to tell you how to use that to count. Okay? And here is the idea. You let mu be the, let's say, uniform distribution over the bases. So let's say I can sample from mu. If I can sample from mu, I can sort of estimate marginal probabilities of the elements. How do I do that? I just generate enough samples, and then I see how many times this element I is in my random base, and you can just keep, you can use laws of large numbers or strong concentration bounds to say that, okay, you can estimate this very well. Now, once you have this, okay, what do? You fix a base B. You say, okay, what is probability of B? Is just 1 over the number of bases because I have a uniform distribution. On the other hand, this probability, let's say B is 1 to R, it's just probability of 1 times probability of 2 condition on 1, and so on and so forth. So I just need to estimate this product. Now each of the elements here is just a contracted matroid. So if I have an algorithm that can count bases of, or I can sample bases of any matroid, and I can sample from all of these matroids, so I can estimate all of these quantities. I would suffer a loss of 1 over epsilon over r each time, and that altogether I would pay 1 plus epsilon r. Okay.
So what happens to the oracle? How does the oracle know the contraction?
Oh, you mean for the independent set oracle?
Yes.
Oh no. No. You mean the oracle for sampling the random base?
You said you know this matroid as an oracle.
Yes, I know the matroid as an oracle.
How do you know the contracted matroid as an oracle? Is this something
So for the contracted Matroid, you can if you have an oracle for the original Matroid, for the contracted Matroid, you always have to have that element, right? So you can just construct a new oracle. If that element is not included, then it's certainly not a base, not an independent set. If it is included, then you just ask the original oracle if, yeah.
The queries you generate make sure that you stay in the contracted or truncated Matroid.
Yeah. There's just one technical thing here. You have to be careful that in order for this to work, you need the marginal probability to be at least 1 over poly of n. But OK, you can get around that. So don't get confused with that. Anyway, so OK, so that.
Same question, sorry, but I mean, OK, you could sample to find P1, but then how do you sample to find this conditional?
You just know that from now on you always assume that 1 is in.
You ask queries in which one is in.
Yes.
I thought the only thing you have is a black box that samples the uniform distribution.
Yeah, for every Matroid. You have a black box that given, so I'm assuming for every Matroid you have a black box that given an oracle that samples the independent set of that Matroid, it samples it gives you a uniform random base of that Matroid. Okay. Good. There's one more thing, that this algorithm is also very robust to noise. So if this oracle doesn't generate a uniform random base, but sort of approximate uniform random base, still everything would work. Anyway, so let me tell you one more thing before I tell you about results. So OK, who cares about this problem? So I want to give you 2 examples. One is sort of so-called reliability problem. So what is this problem? Let's say you have these sort of programs or jobs you want to perform, and there are these machines. If there's an edge, it means that this machine can perform this job. And now we are in a situation that these machines may fail. So let's say this machine fails with probability 1/3, this one fails with probability 1/2, and so on. So what can happen? For example, in this case, the 2 bottom machines fail, the top one survives, but you cannot do all of the jobs. However, if just the middle one fails, you can do the job because there is a matching, perfect matching from the jobs to the machines. Okay. So in the first case, we are not happy, like we don't get to do the job. In the second case, we can do, but now you can see there are exponentially many possibilities, and the question is, okay, what is actually the probability, or can you approximate the probability to do all of the jobs? And that's something you can do if you can count bases of a Matroid. Okay, so you can construct some Matroid. This is called the transversal Matroid, and using like counting independent sets and bases of that Matroid, you can solve this question. Here is another application for coding theory. So let's say you have a parity check matrix. They have this matrix M, and X is a code word if and only if X is in the kernel of M. Okay. Now suppose that you're sending this message X. Some bits of X will be erased. Okay. Maybe here these 2 bits are erased, and now you want to see, can you recover the erased bits? Okay. It turns out that you can recover these erased bits if and only if the corresponding columns are linearly independent. I mean, one way is if they're not linearly independent, there's definitely 2 solutions, so there's not a unique solution. And on the other hand, if they are linearly independent, you can see that is always at least one solution. So basically now the question becomes, how many linearly independent subsets are there? Okay, if, for example, I may know that each bit will be erased with some probability p, and then I want to see what is the probability that I can recover the code. So I just need to know how many linearly independent subsets of these columns exist. And that, again, you can study using this type of algorithms. OK, good. So enough about applications. There are a lot of works related to this. So these works all study special cases of this problem for different Matroids. Just this column are special cases for the graphic Matroids. OK, there are many others about like what can you do with deterministic algorithms, like positively, or some generalization like weighted linear Matroids, like determinantal point processes, and so on. So let me not go into details in the interest of time. Let me go to the result. So this is the main result, that you can get one. So you can get a 1 plus epsilon approximation for counting number of bases, or for sampling a uniformly random base. So this FPRAS is not a good acronym, but it's a technical acronym. It's typically used in these lines of work. It's called, it means fully polynomial time randomized approximation scheme. So that's what it means. But basically what it means is that you can approximate number of bases within 1 plus epsilon, or you can generate a uniformly random base. Okay? Any questions? Okay, so before telling you about proof ideas, let me tell you some direct implications. So the first implication is that not only you can count bases, you can count independent sets of any matroid. How? Just by truncation. If I truncate my matroid, like let's say my matroid has rank R. If I truncate it to K, now bases will be all independent sets of size K, so I can count them. So in particular, you can count number of forests in a graph. Before we knew how to count number of spanning trees. Actually, we can count that exactly. Now we know how to count number of forests with K edges. You can study this sort of reliability questions I was talking about. And basically, to study that, you want to look at the dual matroid and count independent sets of the dual matroid. And that gives you the reliability polynomial. The dual matroid is just the basis of the dual matroid are complement of the basis of the original matroid. But OK, you don't need to know it for this talk. Here's the third application. So there was this old conjecture of Mihail and Vazirani, which says the following. So remember, I talked about this polytope of the convex hull of the indicator vector of all bases of the matroid. This is a polytope, like a high-dimensional polytope. Think of this as a graph, okay, where vertices are just the bases. And remember, two bases are connected if basically, I said the edges are like 1i minus 1j. So two bases are connected if their symmetric difference is 2. So this conjecture was that the graph you get has expansion 1. Okay? An expansion, okay, let me show you an example in action. So here is one example. Let's say you have a matroid, this is so-called a partition matroid. So you have 3 buckets. In each bucket, you have 2 elements, a blue and a red. And you can choose 1 element from each bucket. So there are 8 bases, like blue, 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 red, blue, blue, and so on. And you have an edge between 2 bases if they differ in exactly 1 location. So the graph of the convex hull will be exactly the hypercube. And here the conjecture is that this graph has expansion 1. And we know that hypercube has expansion 1 because if you cross the cube in this dimension cut, like between the left and the right side, you exactly cut 4 edges, and there are 4 vertices to the left. Okay? So it has expansion exactly. Okay, good. So definition of expansion is the minimum of, let's say, call it h of s. Okay, h of s is the number of edges from s to s complement over size of s. And expansion of the graph is the minimum of the expansion of all sets over sets of size at most 1/2. Yeah, it's so-called sort of analog of isoperimetry in the continuous version. Yeah. Okay. So basically, yeah. Actually, so one thing is that this is a very this is a very tight conjecture, and we get exactly the same number 1. We cannot. There is no room to improvement or here. The minimum.
It follows from your result.
Exactly, it follows from the result, and you should, so there is some part of the result which is tight. I'll tell you later, but and which exactly gives you the constant 1. But it's good to keep in mind that hypercube is a tight example for many of the things I will talk about. Anyway, so here are the stuffs I want to talk about. So we're going to learn about these things, hopefully. So I'm going to start by talking about log-concave polynomials, and then we'll see about random walks and simplicial complexes. So let's start with log-concave polynomials. But before that, I want to tell you how the previous works on this problem work. So there is this classical idea to design algorithms like counting algorithms, or to study expansion, like in a hypercube, it's called canonical paths. Basically, what you do is that you construct paths between each pair of vertices in your graph, such that these paths have a small congestion.
Well, before that, you want to say that you have a Markov chain whose mixing you want to analyze, and that's a way to analyze.
That's a way, but let's say you just want to study expansion of a graph.
Okay.
Let's say you just want to study expansion of the hypercube. How do you prove that hypercube has expansion 1 or good expansion? Like one way is to do the following: is to construct paths between each pair of vertices in the hypercube such that the congestion of the paths is small. So what is the congestion? It's the number of paths that go through a single edge. Okay? So you can formalize this, but basically the thing is, if you can construct paths between all pairs of vertices, that for every edge goes constant fraction of the path, 1 over, the right. So basically almost all edges get almost the same amount of the same amount of paths. Then your expansion will be perfect, will be like 1. So how can you do it for a hypercube? You can do it as follows: like given 2 vertices, say red and blue, you choose a random ordering of the bits, and then you correct them one by one. Here's another way to see it. You look at all ways to go from here to there. There are these 3 possibilities. You choose one of them uniformly at random. Maybe you go this way. Then you look at all possibilities. Maybe now there are 2 possibilities. You choose one of them uniformly at random. And now there's only 1 possibility, so you go there. Okay? So basically you get this random path from here to there. And this idea you can actually generalize not just to hypercube. You can also generalize it to Matroid. And basically the point is, this idea, like having a small congestion, works if and only if kind of you have this property that, let's say you look at hi and h of I red and I blue. I red, I mean vertices where the I speed is red, and I blue are those where I speed is blue. This works if and only if there is a perfect matching or a fractional perfect matching from red to blue, from I red to I blue. Okay, if that's true, then you can do this routing, and the congestion will be small. Okay, and the question is, when does that work? It works if a distribution that you're going to study, or you can, for example, study the uniform distribution over the vertices of the hypercube, and then it's going to be uniform over bases of a matroid, if it has some sort of negative dependence or negative correlation properties. Okay, I'm not going to define this formally, but let me just define something. So there is this property called negative correlation, where you say that a distribution is negatively correlated if the probability of I times probability of j is more than the probability of I and j. Being in the base, yes. Another way to think about it is that probability of I condition on j. So when you condition on j, the probability of I only goes down. If j is in, the probability of I goes down. It decreases the probability of I. This is called negative correlation. And there are this family of matroids called balanced matroids, which basically they are negatively correlated. And if you contract them, or if you do contraction or deletion, you also get negative correlation. And okay, but there are these lines of works that basically show that, like this work of Feder and Mihal, which shows that if you have this negative correlation, with this basically balanced matroid, you get negative association. I haven't told you what it is. You don't need to know, but okay, think of it as like having this perfect matching. You're going to get these perfect matchings in this routing, and then once you have negative association, you're going to get the Feder-Mihail conjugate, that the expansion of the graph for the matroid is 1, or that you can count a number of bases of the matroid. Okay, so basically, okay, the simple message is that if you have negative correlation, everything is fine, everything works out. But there was actually a conjecture that all matroids are negatively correlated back in '75, but if you do some simulations, you see that it's actually completely false. Like you can construct matroids with 8 elements, that this is false. Okay, so you don't have negative correlation. In fact, most matroids don't have negative correlation. So what can we do instead? Here's the main hammer that we use. It's called log-concave polynomials, or strongly log-concave polynomials. So let me tell you what they are. Okay.
Is it enough that the log-concavity holds for most pairs, or is that something?
I'll say something about that in a, yeah. I'll say something about that in a slide. Okay, so let's say you have a polynomial or a function in general. You say this polynomial or a function is log-concave if the logarithm of the polynomial is a concave function, or in other words, if the Hessian of the log is negative semi-definite at every point x with non-negative coordinates. Okay, so you can evaluate the Hessian at all points, but I'm saying if you evaluate it at positive orthant, the Hessian of the log is a negative semi-definite matrix. Okay, so this is called log concavity. We say a polynomial is strongly log concave if this is true for all partial derivatives of the polynomial. Okay, so not only the polynomial is log concave, if you take derivatives like with respect to the first, second, everything you do, you still get log concave polynomials. Okay, so this is just a definition. Now here is the main machinery. We proved that. So this is an earlier work of us where we showed that the generating polynomial of any matroid is a log concave polynomial, a strongly log concave polynomial. So what do I mean by a generating polynomial? You just sum over all bases of your matroid the product of zi for I in that base. Okay, so this is like, think of this as the generating monomial of a base. This is just summation over all bases. So this is a strongly log concave polynomial, meaning that not only it's log concave, its derivatives are also log concave. Okay, so just some remarks about this. First of all, like, this is easier to prove if you have a graphic matroid. In that case, basically this polynomial is just something like this. It's just determinant of such a thing for PSD matrices AI. And this polynomial, like log det, we all know is a concave function from optimization. So in case of graphic matroids, this is sort of easier. But the proof of this builds on this recent works on Juni Ha with Karima De Perisetto and Eric Katz, who study these log-concave sequences on matroids. Okay, so there is this heavy machinery on Hodge theory. We use that to prove this. Now there are simpler proofs of this, but the original proof we used here. Okay. Any questions? So now let me tell you some applications of this. Why is this useful? So first, let me tell you what's the difference of. So far I said that the Hessian of the log is negative semi-definite. Let me say the connection between the Hessian and the Hessian of the log. Okay. So we said this. We say you have a polynomial, we have a log concave polynomial. Here is a simple observation that the Hessian of the log is exactly this. Is exactly G times Hessian of G minus the gradient transpose. So this is a rank 1 matrix, and this is the n by n rank 1 matrix, and this is also G is a scalar, and this is a Hessian is an n by n matrix, and also divided by G squared. That's also a scalar. Okay, so this is identity. You can just verify it. Now, what does this give us? Okay, so it gives us the following. It gives us that this matrix, if you know that this matrix is negative semi-definite, you can move the rank 1 matrix to the other side, and you get that the Hessian is less than or equal to a rank 1 matrix in a PSD sense. So in particular, this says that the Hessian has at most one positive eigenvalue. Okay, there's just one thing you have to be careful. So okay, I want the polynomial to have non-negative coefficients. Basically, it's easy to see if your polynomial is strongly log concave, it must have non-negative coefficients. So basically, everywhere you can assume your polynomial has non-negative coefficients. The coefficients, again, remember, say the probability of choosing a base, basically, so they are non-negative. But anyway, so the thing is, this G and this G squared are non-negative, so these are just numbers. You can forget about them, and that basically says you that this identity is true. Okay. So Hessian has exactly one positive eigenvalue. In fact, it has exactly one, not at most one, because its entries are non-negative as well. So in fact, the converse of this is also true. If your polynomial is homogeneous, you can start from this fact that the Hessian has exactly one positive eigenvalue to go to that fact. Okay? So this fact is actually very related to what you get, things you get from Hodge theory. So you can basically go from that to log concavity. Okay, so now let me tell you a simple application of this log concavity. Oh, so W? Sure, sorry. But that's W, A, and G. So yeah, so you can use log concavity to prove approximate negative correlation. So I said that matroids are not negatively correlated, but they're approximately negatively correlated. So here is a theorem of Ha and Wang that for any matroid you get approximate pairwise negative correlation, meaning that the probability of ij over probability of I probability of j is at most 2 as opposed to 1. Okay? And in fact, this is another observation we made later on, that if instead of this, you look at average negative correlation. So you choose I and j uniformly at random. You look at correlation of ij versus pi pj. This is very close to 1. It's like n over n minus 1. Okay? So even though you're not negatively correlated, you're not really very far from it. Yes?
So if you fix I and look at the expectation over j?
Yeah, I thought on that. I don't know how to. Yeah, I don't know how to. I think it should be true, but I don't know how to get. I think you should still get like something like 1 plus 1 over n, but yeah, I don't know how to prove that. You know. Anyway, so how do you prove this? Basically, it just follows from what I said in the last slide, that you need to make two observations. Okay, first you normalize g such that g of 1 is 1. So let's say the coefficient of a base is 1 over the number of bases. Then it's not hard to see that the coordinates of the gradient, if you evaluate it all once, give you the marginal probabilities. The ij coordinate of the Hessian will give you the joint probability, like probability of I and j. Now, okay, so now you just use this identity. You plug in. Okay, so this is true. So you just plug in some vector x. So this is true for every x. So you choose x carefully to be like 1 over pi, and then you do some calculations. You get that. Okay. So this was sort of the beginning of our project. So it was like, okay, we know that negative correlation is useful. We know that you don't always have negative correlation, but we know that there is this nice thing that you have, like approximate negative correlation. So maybe you can use the approximate negative correlation to prove some approximate negative association and say everything would work as follows. But I don't know. I mean, I tried. The best I could prove was to get an exponential loss in n when you do approximate negative association. So this, again, I haven't said what negative association is, but it's basically this perfect matching or fractional perfect matching you want between hi and h of I red and I blue. Okay, so that way doesn't work. Yes.
Is this too tight for that factor too?
That's also a good question. I think Juni has a conjecture that it must be 8 over 7, but we don't know. Right now, 2 is the best we know.
We know a lower bound of 8 over 7.
We know a lower bound of 8 over, yes.
If it's true, it should be best.
Okay, so now let me tell you about random walks. So this part should be quick. I suppose most of you are familiar with random walks. So basically, I want to talk about random walks on weighted graphs. So let's say you have a weighted graph G. When you do a random walk, like from a vertex, you choose an edge proportional to the weights of the edges. So from 1 here, I choose 3 with probability 3 over 1 plus 2 plus 3, which is 6. So I choose 3 with probability 1/2. So this is called a non-lazy random walk.
Just for should not be confused with the graphs that in the graphic matroid. The graph we're talking about is a graph.
This is a generic graph. It has nothing to do with matroids at the moment. Yes. Then, if you run this random walk, it has a stationary distribution. It converges to a stationary distribution, assuming some conditions, but let's not get, assuming some connectivity. So it must be connected and non-bipartite. Assuming those, it's going to converge to a stationary distribution where the probability of every vertex is proportional to its weighted degree. Okay? And there is this fact, okay, I said the random walks basically converge if the graph is connected and non-bipartite. And this non-bipartiteness is not so important. You can usually relax it by adding some self-loops. So you can, you can add a self-loop at every vertex, you make random walk slightly slower, but everything will be, then you're going to converge to the stationary distribution. Okay, so that's about random walks. Now, let me tell you about mixing time. So I said that if you run a random walk, it's going to converge to the stationary distribution. The question is, how long does it take to converge to the stationary distribution? That's the way we're going to characterize that is by using this notion of the mixing time. So let's say that's typically the way you define it. You start a random walk from some vertex I. You look at the L1 distance of the stationary distribution and the distribution of the walk started from I at time t. And the mixing time is basically the first time that this L1 distance is at most epsilon. So this is called the mixing time starting from I with respect to epsilon. And there is this classical theorem that if you have a graph G, if you know the eigenvalues of the random walk matrix, you can construct a transition probability of the random walk. If you look at the eigenvalues of that matrix, the mixing time is at most this much. So in the numerator, so this epsilon is not usually important, forget about it. You have log of 1 over pi star, where pi star is the state with the smallest probability, over 1 minus max of lambda 2 and lambda n. Okay? So lambda 2 is the second largest eigenvalue, and lambda n is the smallest eigenvalue. Again, you can usually, this lambda n is not usually a big deal. You can add self-loops, make sure that lambda n is non-negative. So usually the main important thing is 1 minus lambda 2, is the so-called the spectral gap. Okay? So here is the message you want to have in mind. If you have a graph that lambda 2, let's say, is less than 1/2, it mixes very rapidly. It mixes basically in, let's say, if the stationary distribution is uniform, it mixes in log n or 2 log n time, something like that. Okay?
And this log is important because the graph will be exponential size, and we want
exactly
time.
Exactly. So the thing is, yeah, the graphs we're going to talk about will have exponential size. The log in the numerator is not so important because, okay, log of exponential is a polynomial. The denominator is the important thing. So you really want this spectral gap to, so if I give you a graph of for any graph, you know that lambda 2 is at least 1 minus 1 over n cubed. So this difference is always at least 1 over n cubed. So, but if the number of vertices is exponential in, let's say, as in the Matroid case, in the number of elements, this is a useless bound. So ideally, you want lambda 2 to be like, bounded away from 1, like something ideally like 1/2 or maybe 1 minus 1 over n, like the number of elements of the Matroid or so. Okay. But before that, before telling you the algorithm, I want to tell you one more thing. So I told you about this log-concavity. I haven't told you why is it useful. I want to show you one slide of a random walk where log-concavity is useful. Okay. So here is one way that log-concavity can be useful. So let's say you have a Matroid. I want to construct a graph and run a random walk on that graph. Okay. So I want to say this random walk mixes. It's not gonna allow you to sample bases, but it's gonna be a useful random walk, as we will see later on. So let's say you construct this graph G with n vertices. N is the number of elements of your Matroid. The weights I want to put based on the Hessian matrix, the Hessian matrix of the generating polynomial of the Matroid. Okay. Evaluated. Sorry, should have been 1. Evaluated 1. So basically, the weight of I and j is exactly the number of bases that have I and j. Okay. Okay. So this is going to be my adjacency matrix of my graph. You can run the random walk. The point is, since the Hessian matrix has at most one positive eigenvalue and exactly one positive eigenvalue, when you normalize it, the random walk matrix the second eigenvalue will be 0 or negative. So the random walk matrix would have at least one positive eigenvalue. So the spectral gap is huge. It's like 1. Okay? So here is one example. Look at this. This is a matroid. This is the generating polynomial of a matroid. This is the Hessian matrix. And this is the graph. And basically the point is, if you look at this Hessian matrix, this is going to be the adjacency matrix of my graph. It has the second eigenvalue is less than or equal to 0. It's non-positive. So the random walk on this graph mixes very rapidly.
We just don't know how to run the Markov chain.
Yeah. So this is a random walk on a small number of an n elements. I want to use it to talk about a big random walk, a random walk on all bases of the graph. Okay. So that's where simplicial complexes will be useful. So let's talk about simplicial complexes. Okay. So what's a simplicial complex? It's basically a downward closed set of elements. Okay. One famous example is the clique complex, the set of cliques in a graph. If you have a clique, any subset of it is also a clique. So it gives you a simplicial complex. Another example I'll say more about in the next slide is the independent sets in a matroid. If you have an independent set, every subset is also independent, so it gives you another simplicial complex. So these are some terminologies. You can study a face or a set. You usually use this thing. You can, in the Matroid language, this is an independent set. We usually define a dimension to be the number of elements in that set. Usually in the simplicial complex, this is defined to be this minus 1, but I prefer this notation because of my application. But anyway, so it's the number of elements in that set. The dimension of the simplicial complex is the largest, is the set or the face or the independent set with the largest size. So this is exactly the rank when you talk about the Matroid. You can think about the graph as a two-dimensional simplicial complex. One, like dimension 1 faces are vertices, dimension 2 are edges. I want to use this notation to denote, faces of the complex of size k. We say a complex is pure if maximal faces have the same size. It's not pure otherwise. So here you see two simplicial complex. This one is not pure. This one is pure. So this one is not pure because if you look at 2, 3, it's a maximal face, but the face of the largest size is 1, 2, 4. Whereas in the right one, it's pure because the maximal faces all have size 3. Okay.
But for matroids, they're all pure.
Exactly. For matroids, so this is basically what you get for matroid. Independent sets are faces. Exchange property in the matroid tells you that they are pure. The independent set complex is a pure, and the rank is just a dimension. Okay. Now that you have a simplicial complex, so you have this huge thing. You can study it. You can study random walks on it, and this is basically what I want to talk about. So I told you this identity that if second eigenvalue is small, random walks mix rapidly. Now there is another story going on, independent of all these works on matroids, so there is this large group of people studying, large community of people studying high-dimensional simplicial complexes, and the point is you want to generalize a notion of a expanded graph, a graph which has this property to high-dimensional simplicial complexes. And so basically, this is a line of work where you say, okay, you study Laplacians or random walks. You say if localized random walks are good. I haven't told you what this is, but localized random walks are sort of similar to the random walk I just showed you on a matroid, okay, which I told you it's very good. And they basically say if localized random walks are good, then you have a high-dimensional expander. I'm not going to tell you what this is, but think of some analog of this. And then there are some recent works that kind of say that if you have high-dimensional expander, then you can study random walks. So similar to the fact that on expanders, you get very fast mixing. On high-dimensional expanders, you also get very fast mixing. So basically what we show is that if you have log-concavity or strong log-concavity, you can get this, and then you can go so far. Okay? So
it's very important that you get very close to 1 because there the half plays a very important
yes, I'll show all of that. Okay, now let me tell you the algorithm. Let me tell you how to move on a high-dimensional simplicial complex. So let's say you have a simplicial complex X. You can construct a bipartite graph. Oh, this should have been, sorry, this should have been G of R. You construct a bipartite graph on independent sets of size R and R minus 1. Okay, so here these are like bases of my matroids and independent sets of size R and independent sets of size R minus 1. Then what I do is that I just run a random walk on this graph. So what I do is that maybe I start here. I look at all of the neighbors of this guy. I choose one of them uniformly at random. Maybe I choose this guy. Then I look at all of the neighbors of this guy. Now there are 2. I choose one of them uniformly at random. So I move to this guy, and so on. I choose look at the neighbors, choose one of them uniformly at random. Oh, this should also be red. But OK, so I go to here, and then I look at this. In this case, I have only one neighbor, so I go back. So the thing is, this is sort of a lazy random walk. You may go back to where you come from, because when you come down, you can go back to where you come from. The other thing you want to notice is that if you look at the degree of everybody at the top, it's exactly R. Why?
It's pure.
No, not pure.
It's a rank of the matrix.
It's a rank, because it's a simplicial complex, because there are exactly R ways to remove an element from somebody in the top. So that gives you exactly R neighbors down. So if I run this random walk, the stationary distribution at the top is uniform. Okay? Because all of them have the same degree. The stationary distribution at the bottom is not uniform, because the degree is not necessarily uniform. And in fact, it will come in a second, but at the bottom, the probability of a vertex is the number of bases that contain that element. Okay, so that would be the stationary distribution in the bottom. The other property is that again, you can say that this graph is a connected graph. So again, you can use exchange property of Matroid, say this is a connected graph. So the random walk actually will mix to the stationary distribution, to the uniform stationary distribution. So this is exactly my random walk. This is exactly my algorithm. I start from a base. Each time I remove a uniformly random element, go down, then I look at all of the bases that contain this guy. I choose one of them uniformly at random and go to the top. So I just do it. So the whole process is to analyze this operation. Okay. So here is the main theorem that we say that. Okay. So here's the main theorem. We say that for any matroid. So this, I defined this, right? So this is okay. So I called this the transition probability of this Markov chain, and this notation means that you go down and then go up. Okay, and R means that you start from up, you go down, you go up. Okay. Sorry, this should have been down up. So P of down up of R. This is a PSD matrix, and the second eigenvalue of this down up matrix is at most 1 minus 1 over R. So the first eigenvalue is 1, the second eigenvalue is 1 minus 1 over R. So the spectral gap is 1 over R. So that tells you that basically you just pay the spectral gap, which is 1 over R, times the log of the number of states, which is at most n choose R. So you pay, your mixing time would be basically R squared log of the number of elements, R squared log n. In addition, you can prove more things, that you have at most this much eigenvalue of value, at most that much. So not only, basically the eigenvalue pattern is very similar to what you see in the hypercube. You have like R eigenvalues, which are 1 minus 1 over R squared-ish, which are like 1 minus 2R, and so on and so forth. Sorry, this should have been, again R. I changed D to R at some point, and then yeah, this is R. Okay, so basically once you have this, you get FP-RAS for uniformly sampling basis of any matrix. Any question? So, okay. So again,
chain is easy to guess, but somehow proving that the
good. So let me tell you the first observations about this Markov chain. So again, this is my Markov chain. Let's look at this matrix. This is a PR matrix. So basically, the Markov chain I was studying on the top, right? By studying a two-step Markov chain where you go down, then you go up. You can actually first study the whole transition probability matrix on the full state space. So let's say this is PR. It has two matrices, PR minus 1 up, where you go from here up, PR down, where you go from up to down. Okay, so this is the transition probability matrix on the whole bipartite graph. Okay. Now, what I did is that I look at a two-step random walk here. A two-step random walk is just PR squared. Okay, so what do? Either you start from top, you go down, then you go up, or you go start from down, you go up, then you go down. Okay, so these are the two possibilities. And this exactly gives you these two matrices. If you start from up, this is PR of down up. If you start from bottom, it's a PR minus 1 of up down.
But it's on the bottom you start from not a fixed element, but from the stationary
No.
distribution.
You start from a fixed element. From fixed element,
So
you
it's
start.
not uniquely defined.
What is not uniquely?
This PR1. Well, anyway, you define it to be start from a particular element.
No, from all. This is a matrix. You start from all. You start from here. You go up. This is just this matrix.
Fine.
It's a transition probability matrix.
Why is it on this diagonal and not the?
Oh, because it's a bipartite graph. So you don't have edge. So you don't have edge from top to top or from bottom to bottom.
But aren't you going to go down and then back up, so you're going to end up on the same side?
This one. Sorry, this one should have been on the other. You're right. That one should have been on the other side. Yes. Good. Yes, it's really this thing. It's really PR. Okay. Thanks. So now here is the point. Because you have this, you know that PR squared is a PSD matrix. It has non-negative eigenvalues. So in particular, it says that both of these matrices are PSD. So they have non-negative eigenvalues. Secondly, because these two you get this factorization of these two matrices, right? One of them is this one of them is the other. So these two matrices have exactly the same eigenvalues. So this is a simple fact in linear algebra that AB and BA have the same eigenvalues. So lambda 2 of PR down up is equal to lambda 2 of PR minus 1 up down. So if I want to study this, I can just study the other one. Now this just immediately study, maybe I can do induction. Instead of study the R, maybe I can study R minus 1 and then do induction. Okay, so that's what I want to do. Okay, so let me tell you now the more general story. So you can extend this graph down. This was at level 3, 2, 1, and so forth. First of all, remember that I said the degree here is the number of bases that contain that element. So when I want to analyze this walk by walk in the next level, I want to make sure that at the next level I have the same stationary distribution on these guys. Okay? So you need to define a weighting on your graph. So what would be the weighting? You define a weight of 1. You define a weight of 1 on all of the bases. And then the weight of everybody would just be summation of the weight of the next level. So the weight of this guy would be 1 plus 1, 2. The weight of this one would be 1 plus 1 plus 2, 4, and so on. Another way to see it is that the weight of everybody is just the number of bases, is just the number of bases that contain that person. So here you can normalize by 2. You get a normalizing factor, r minus k factorial at level k, and the weight will just be like there are 2 that contain this guy, there are 3 that contain that guy, and so on. Here the normalizing factor is 6, so there are 3 that contain the empty set, which are all the 3 bases. Okay, so you get that weighting. Now, once you define a weighting on all of the bases, you define the weight of the edge to be the weight of the upper base, the base on the upper side. So the weight of this edge would be 2. The weight of this edge would be 1. Now I can run a Markov chain on this graph. Okay. So similarly, you define everything. You define a transition probability matrix on the union of xk minus 1 and xk. Lambda 2 of pk down up is equal to lambda 2 of pk minus 1 up down. And the main lemma is just this. It's just that pk of up down is at most the average of pk down up and I, where you average out with respect to k plus 1.
And this is true for any pure simplicial complex.
This is no. This one is not. This one. This is for matroids only. Before this, everything works for any pure simple.
For the high-dimensional expanders, they have a similar relationship between the run.
There is a loss here, yes. So there is a loss there. For matroids, you get this, but before this, it works for all of those. So basically, many of these language and these things are borrowed from those works on high-dimensional simplicial complexes. But this one actually works for matroids. So basically, okay, now just assume these two facts for every k, and you can do the induction. You get that basically lambda 2 of p1 when you do in the first level is at most 1/2. Then lambda 2 of, you can use that one, it's at most 2/3, 3/4, k over k plus 1, and then you get that lambda 2 of pr is at most 1 minus 1 over r. Okay.
Hard to prove this?
That's really complex. So it's not. This actually corresponds to. I'll say in a second, but it actually corresponds to log concavity. That's exactly what log concavity tell you. And before that, let me tell you one more notation in this, one more definition in this language. So you can define a link of a simplicial complex, a link of a face of a simplicial complex, where what you do is that, let's say I look at 4, I look at all faces that contain 4, and I remove 4 from them. So here, 1, 2, 4 contain 4, so I remove 4, I get 1, 2, 2, 3, and so on. So this is a link. Here is another example. You look at this graph. You look at the face. Say I look at 2. Now, I look at everybody that contains 2. So these are the independent sets that contain 2. I remove everybody else. I delete 2. Okay, so I get, so this is my link. Okay. Now you see naturally the link defines the graph. I can basically, okay, this can go up, but I can just look at the first 2 levels of this. This is a bipartite graph. Or I can even look at it as a graph. Just look at these guys as edges between 1 and 3 and 3, 4, and so on. So a link defines a graph, and that graph is called one skeleton of a link. It's just you look at the faces of dimension 1 and 2 in the link, and then construct the graph on them. So here is one nice example. Remember this partition matroid example I told you at the beginning? Let's look at the link of 1. So what is the link of 1? So I'm going to have 1 of red. Now I can have, from everybody else, I can choose whatever bases. So I have all of possible bases which choose exactly a red or a blue from each bucket. There's not going to be any edge between like 3 and 3 of this, 3 and 3 or 2 and 2. But between every other pair of vertices, you're going to have an edge. And the weight of that edge you can compute is exactly this number. This is exactly 2 to the n minus 2 is exactly the number of bases that contain 2 and, like this 2 and 3, for example. This is just a normalizing factor. The n minus 2 factorial just comes from the way we do the weighting. So you get this complete multipartite graph. You get this complete multipartite graph, and every edge has that weight. Now you say you have a local spectral expander. If every link, if the random walk on every link has second eigenvalue lambda. So there's just one technicality. This p tilde, I mean the non-lazy random walk. So the non-lazy random walk on every link has second eigenvalue lambda. So in particular, in the case of this hypercube and the corresponding link, here the second eigenvalue of a multipartite graph is 0, that's something you can check. So that says that a simplicial complex you get here is a 0 local spectral expand. The point is this is true not only for this, but in fact for every matrix.
With 0?
With 0, yes. So this was not a special case about the partition matrix. This is actually the fact for every matrix.
Yeah, it's a non-lazy, so it can have negative eigenvalues.
Yes,
Yeah,
it can have.
It's the analog of expansion 1.
But here lambda 2 is not the second absolute.
It's the second absolute. It's not the absolute value. It's the second eigenvalue.
Right.
0 in absolute value is still 0.
No, I understand, but it's not second in absolute value. It's not second rank in absolute value. It may be negative.
Yeah, it could be negative. Yes, yes.
Yeah, right. Sometimes you can.
So here is basically the way the proof works. So I said that we just need to prove this. Basically, the point is a strong log-concavity implies 0 local spectral expander. And here is the other fact. The other fact is that if you look at this, so the difference of this and the right-hand side, it's exactly equal to summation of the localized random walks. This notation means that you drop the top eigenvector, the eigenvector of all ones. So you project your localized random walk on a link. This is a random walk on the one skeleton of the links, right? So you drop the eigenvalue 1. You just look at it. You just look at the rest of the eigenvalues, and now you sum over all of the links, all of the taus in k minus 1. The sum is exactly equal to this.
Maybe high-level language is the local to global.
Exactly.
If all the local links are expanding, then you're globally an expander.
Exactly.
And that goes back. I mean, they proved it for this generality, but it goes back to Garland.
To Garland, yeah. So this type of things originally goes back to Garland. That if local things are good, then you get global things.
Yeah,
basically.
Very good.
Yeah. That's the main problem. It should be so. So here we are very good. We are 0. This proof can actually tolerate a little bit more. It can tolerate 1 over k-ish. 1 over the dimension of the simplicial complex, and it can only go forward, but not much more. You cannot. It doesn't tolerate like 1/2. If this was 1/2, even though in the actual graph it was good, here it won't be good. Okay. So, okay. Let me just. I just wanted to give you one slide why this is true, and then I'll be done. So I want to say why matroids are 0 local spectral expanders. The thing is, okay, let's say you have a matroid. X is the independent set complex of the matroid. You look at an independent set tau with k elements. Let's say this partial tau is that you differentiate with respect to I in the independent set tau. So this operation is basically contraction. If I apply this operation to the generating polynomial of the matroid, I'm contracting the independent set I, and I know that after this contraction, I still have a log-concave polynomial. So here is what I do. I look at this tau. I do the operation. I know that this is log-concave. So the Hessian has at most 1 positive eigenvalue. So the second eigenvalue of the Hessian is non-positive. Okay? Now, the nice fact is that the ij entry of the Hessian is exactly the number of bases that contain tau, I, and j.
Sorry, what are you trying to prove?
I'm trying to prove that matroids are 0 local spectral expander, right?
So you already know that the lambda 2 is small. Now
I know lambda 2 of this is small. I want to say lambda 2 of the random walk is also small. So I want to say that this matrix basically gives you the random walk matrix. And the point is, the point is this matrix is just the adjacency matrix because the ij entry is exactly the ij entry of the adjacency matrix, exactly the number of bases that contain tau, I, and j. So these two are exactly the same, the Hessian and the adjacency matrix. Again, there are some normalizing constants, but they're basically the same. So this says that adjacency matrix has exactly 1 positive eigenvalue. So when you normalize it and get the random walk matrix, the random walk matrix second eigenvalue is non-positive. And that's what you get. Yeah, so basically you can generalize this to all polynomials, not just simplicial complexes. And you get this nice language between simplicial complexes and polynomials. Like dimension in a simplicial complex corresponds to degree in a polynomial, pure corresponds to homogeneity. When you look at the weight of the empty set in a simplicial complex, it's just when you evaluate your polynomial at all once. The adjacency matrix of the one skeleton is just the Hessian of a partial derivative and then the localized random walk is just a normalization of the Hessian with respect to the gradient. So it's just everything, every combinatorial thing you do, you can look at the analog in the polynomial language.
So here the sampling problem would be to sample the coefficients of the polynomial.
To evaluate the polynomial.
Yeah.
Exactly, to evaluate the polynomial. And that's, okay, so it's that. So that's exactly what you do. If you give me a homogeneous strongly log-concave polynomial, if I can evaluate the coefficients, I can also evaluate the polynomial at any point with non-negative value.
So it generalizes, for example, Gurwitz result, which does it for hyperbolic polynomials using ellipsoids.
For volume polynomial, no.
Volume.
For
hyperbolic polynomials.
For hyper, I didn't know that result, but I know that Gurwitz's result actually has a loss typically exponential in degree. This is 1 plus epsilon.
Not in the we're using the we can talk.
Okay, we can talk about it. Yes.
Is there a way to do it the other direction? If you're going to evaluate G to get to evaluate the coefficient?
To some extent. So Gurwitz, for example, has this result that you can evaluate the volume polynomial. The coefficient, when you have the volume polynomial, the coefficients correspond to mixed volumes. But there is an exponential loss in the dimension. So yeah, in the multiplicative factor. So actually we don't know. So that's actually an interesting question. Can you get 1 plus epsilon approximation for mixed volume? We can estimate the volume within 1 plus epsilon, but we don't know how to approximate the mixed volume of polytopes within 1 plus epsilon.
It's not like hard, it's going to be hard.
No. There are other things we can also evaluate, like there is this Tott polynomial we can evaluate. I don't have time to tell you what it is. You can also raise the coefficients of a polynomial to powers less than 1, and it remains strongly log-concave, so you can still evaluate. Okay. Yeah, so basically this is sort of a short view of what we do. Basically, so our first work relates Hodge theory to log-concave polynomials. Now we can relate these two log-concave polynomials to high-dimensional expanders. There seems to be some connection from. So this arrow, so actually there's actually some proofs of high-dimensional. So you have this theorem, right? That that comes from Ayeshke in your work with Wang. That this matrix, the IJ matrix, the number of bases that contain INJ has at most 1 positive eigenvalue. That we can reprove that using like Oppenheim's theorem in high-dimensional simplicial complexes. So, okay, just some open questions if you want to think about. Can we count? Are these non-broken bases? Like you can ask me afterwards what they are. Can we count them? Basically, they correspond to coefficients of the chromatic polynomial of a graph. Can we improve the running time from R squared to R? There's also a question of studying like stronger bounds, this not the Poincare constant, the Log-Sobolov constant, or the modified Log-Sobolov constant. Can we study these constants for the Markov chain, for the Markov chain on basis of the Matroid? And the other thing is that, so this conjecture of Mihailov and Zerani, that's actually for any 0-1 polytope. That if you have any 0-1, if any set of 0-1 points, if you look at the convex hull, if you look at the graph on the convex hull, it has expansion at least 1. We prove it for the Matroid case. It's still open for the rest of them. No, it is.
One skeleton of any set of points, you take all ones and all zeros, what does it mean? Looking at edges that are adjacent, right?
Yeah, so then it's going to be just, there's going to be direct edge from 0, 0, 0. So, yeah. So
it's not the graph of the cube.
Yeah, yeah.
So what are the points? Yeah, exactly what is. Or you take the convex hull, you take the one skeleton. Good. Okay.
That's the conjecture. The thing is, it's a useless conjecture for algorithmic purposes in many cases. Like for example, for matchings, like perfect matchings, it is proven, this conjecture is proven, but it's a useless conjecture because it doesn't allow you to sample. The edges actually are not, in the Matroid they're very nice, but in general they're not, they don't just change 1 or 2 coordinates, they may change many coordinates.
All right, thanks. Questions?
So the second line, you're saying you think that the mixing time is actually order R log n?
Yeah, so the thing is, so that actually is this, so we can actually study all of the eigenvalues of this thing. And as I said, they match the pattern of the hypercube. So the thing is, in hypercube, the mixing time is n log n. If you just use the second eigenvalue, you get n squared log n. The way you get, there are multiple ways to get n log n. One way is to use the fact that, is to use 2 facts. One is that the hypercube is vertex transitive. And second, that because you know all of the eigenvalues, you can study average mixing time. So average mixing time in the hypercube is good. If you start from a random vertex, it's good because it's vertex transitive. From every vertex, it's good. Our graph is, you can still prove that the average mixing time is good, but because you know all of the eigenvalues, but it's not vertex transitive. So that part doesn't work. Another way to do it is to study like this, log Sobolev constant or spectral profile. These are the things we still couldn't analyze.